Hello, and welcome to Physics 2212, Experiment 4, Faraday's Law. The purpose of this lab is to collect observational data of a magnet falling through a conductive tube of aluminum foil and model the magnet and Rolle's interaction computationally in order to explore the phenomenon of Faraday's Law. Some fundamental principles necessary for this lab are Faraday's Law, which describes a magnetic flux that changes in time and creates a non-Coulomb electric field which generates voltage. We will also need to know about Newton's second law, which states that net force is equal to mass times acceleration, and Newton's third law, which states that for every action there is an equal and opposite reaction. We will also need an understanding of magnetic force, which helps us to understand the force felt on a moving particle by a magnetic field that is being produced. Some assumptions we will use for this lab is we will assume that the tube is fixed whilst using Newton's third law to calculate the force exerted on the falling magnet by the tube in the computational model. We will also assume air resistance is negligible in the computational model. Our system in this experiment is the bar magnet, and the surroundings are the aluminum foil roll. And the main results of this lab are the average time in the tube of the real-world system by the bar magnet is 2.314 seconds, while that in the computational model is 2.168 seconds. The experimental design is as follows. A bar magnet with the north pole is labeled and dropped into a greater than 1 centimeter thick roll of aluminum foil, as seen in the diagram. A video is taken of the bar magnet being dropped, and the process is repeated 5 times in order to determine the average fall time of the magnet. I have also included a drawing of what is happening to better understand the induced current that is being created by the bar magnet, but we will discuss this more later. Trials 1 through 5 yielded an average time of the bar magnet in the aluminum foil roll to be 2.314 seconds. The measurements of the foil roll are also taken to be later used for the computational model. For the computational model, I firstly defined my physical constants and initialized the velocity versus time graph. Then I created the aluminum foil tube as a series of rings stacked along the y-axis and defined the geometry of the tube with the measurements I took earlier. Then I created the bar magnet, defining its mass and dipole moment as observed in Lab 2. I then created a function to calculate the magnetic field of the bar magnet, and then calculated the magnetic flux created by the bar magnet. I then determined the conventional and magnetic forces applied to the bar magnet. Finally, I was able to calculate the net force on the bar magnet using the magnetic force and gravitational force. I was also able to apply the magnet's velocity and position to determine the total time of the magnet spent inside the tube, which was found to be 2.168 seconds. The clockwise current corresponds with the color red, and the counterclockwise current corresponds to the color blue. This is because the induced current is pointing in the positive y-hat direction to combat the increase in flux in the negative y-hat direction. Thus, the blue induced current flows in a counterclockwise manner due to the right-hand rule. If the magnet were to be flipped, the system would remain largely the same. However, the red current representing flux would now be flowing in a counterclockwise manner due to the magnetic moment of the magnet pointing in the positive y-hat direction. The blue current representing the induced current would become clockwise, yet the resistance felt by the magnet and the slowing of its fall would remain the same. The real-world model revealed an average time of the bar magnet in the tube to be 2.314 seconds, whilst the computational model revealed a time of 2.168 seconds. This is a difference of 0.146 seconds. Considering other elements such as air resistance may lead to a more accurate computational model. The velocity versus time plot tells us that when the slope is increasing or decreasing, only gravity is acting on the magnet. But when the slope becomes 0, the force of gravity is equal to the magnetic force of the tube felt by the magnet, and so the net force is 0. If resistivity of the conductor were reduced to 0, the induced current on the tube would increase due to the decrease in resistivity, and thus the magnet would take even longer to fall through the tube. If holes or slots were cut into the tube, the current would decrease. due to the decrease in area the magnetic field may travel through on the roll. This would result in a decrease in magnetic force felt on the magnet by the roll, and thus decrease in fall time for the magnet. Some sources of error in this lab might have included interferences from other magnetic fields and uncertainties/errors in measurements. Ultimately, the computational model and real-world models had very similar results, thus supporting the physical realities of Faraday's laws.